do anything to LLMs having some metacognition. And the general point that we are trying to use human terms to describe what's going on with LLMs is a very valid one. Metacognition is used for humans, but when LLMs display similar behavior, internally there might be something very different going on, which is Rao's point, but from outside it looks like metacognition. Anyway, so I used this idea of LLM skills and metacognition in the opening lecture, and I'll tell you more about it. And the important distinction I made was between facts and skills. That a lot of the early thinking about LLMs was about facts. What knowledge should they have? And in the first talk, I argued that they actually pick up these skills, which are not in the training data, or at least the composition of skills is not in the training data, and they do it very well. And skills should be thought of more like procedures. But again, we're using terms from programming languages or something where procedure is very always correct and so on, right? It's once you write it down. And of course, these skills, like everything LLMs do, can be only applied correctly some part of the time. But the point is that they can be chained together in normal ways. And we saw evidence for that. The skill mix kinds of tests where LLMs can compose, say, 5 skills, and the number of possible combinations is larger than the size of the training set. Okay, so so this was we talked about this, the idea of metacognition, and I'll tell you a little bit more about it. Okay, and this slide you also saw in the first lecture. So I raised the question of, how do we know that humans are aware of what they're doing? And when you read a question like this, and I ask you to talk about how you're going to go about solving this question, you can give a reasonable explanation. And this is called metacognition in humans. And we can tell you about the internal reasoning process. And these are some of the classic works, and metacognition is used to help humans or children learn better. If they have problems in reading, for example, you teach them how to read better. Did anybody have metacognitive help on reading? Do you remember that? It's probably when you were little. No? Okay. So, yeah, when you have kids, you start seeing that again, that the whole metacognitive aspect of teaching. You see their instruction materials and there's metacognition there. All right, so how do you elicit metacognition in LLMs? So I gave just this one anecdotal example in the opening lecture, but here I'll tell you a little bit more. So let's say you have a math data set or physics data set, whatever. These models are pretty good at solving those questions, at the high school level, maybe university level. And so you give it task examples and ask it to label each example with skills. And the format for skill names is sequence of 4 words connected with an underscore. So that's a very expressive way to label skills. So you ask it to label it with skills for each question. And now you take a lot of skill labels from, say, a few hundred questions, and you ask it to semantically cluster them. Now, clustering you think of as something that you do with vectors, right? That's like a basic thing you learn in many courses, like data processing or machine learning. So there's a vector, a high-dimensional vector, and you cluster those, right? Based on what's based on the distance, their interpoint distances. Here, there's no vectors. It's just sequences of words with 4 words, right? Skill names. So the meaning for that list of 4 words, or that sequence of 4 words, is in the LLM's head. Okay, again, Rahul will not like this anthropomorphic phrasing, but we don't. Okay, in its parameters, whatever. So the meaning of these labels of 4 words is entirely determined by the LLM's internal parameters, right? So, and it's going to do clustering based on its internal meaning. So just as we can, right, intuitively we cluster people based on our internal sense of these people. Okay, so it does this clustering, and then you get those clusters, and then you ask it to name the cluster using the same kind of nomenclature list of 4, sequence of 4 words. So that was this paper of ours. Now, this is distinct from works that attempt to identify traces of human skills in LLM activation. That's interpretability kinds of work, and there's a lot of work on that. And in 2023, at the time, that was a paper that had come out a few months earlier. But this is very different. We are completely letting the LLM decide what skills are and how to do them. Okay, we're not imposing the human, at least not explicitly imposing the human framework of skills. So using this method from this famous math data set, these are the kinds of skills that you get. Okay, so geometry, understanding certain properties in algebraic manipulation, other geometric skills, Pythagorean skills, quadrilateral and polygon skills, etc. Now, some of these things, like 3-dimensional geometry, like what kind of skill is that? Okay. Oh, here it is. This one, right? What kind of skill is that? Arithmetic operations. So these skills stand for some region of knowledge in the LLM's internal parameters. Okay, they're not things that mean so much to us. Nevertheless, LLMs do understand each other with respect to this nomenclature. That's what we found. So this skill catalog can be labeled, it can be used as follows. You ask GPT-4 to label each math question using the main skill it uses. Now, remember there is something called K-short prompting. So K-short prompting is you give the LLM, let's say, an algebra question, and you include K-solved algebra questions in context. So now it's a little bit like, when you're trying to do homework. Remember when you were trying to do homework and you're working on a tough question, it helps to have your class notebook or class materials open in front of you where there are other examples of solved questions. And that is a good way for you to refresh your memory of how to solve this question, and then that's helpful when doing it, the homework question. So this is called in-context prompting, and this is a standard thing that's used when evaluating LLMs. So some of the evaluation numbers that you see are using this kind of prompting. And you can now improve this by providing skill relevant in context examples. So if you can label each question with these skills and then provide skill relevant in context examples. And the other uses that this can be used for data selection during instruction tuning. And this was in the last paper also. Okay, similar idea. So this is the concrete numbers for that. So if you use in-context topic-based prompting, that's that line. That's this line. Okay, so chain of thought plus topic-based, you get certain performance. And if you do skill-based examples, you get better performance. So the point of this is that this skill-based classification is more meaningful. Okay, it's a more fine-grained classification of questions based on the skills that they require. And if you use those kinds of examples, tailored examples in context, performance improves. All right. Questions? So yeah, this is the question that arises. Is this metacognition? Now, obviously, it's not like human metacognition; it's something else. Or is it just some parody of math pedagogy? And my guess is that this phrasing is repurposed from human pedagogy, you know, the skills and so on. But these skills are derived from internal analysis of training data. And I illustrated this already. This was a kind of metacognition that I talked about in the first lecture, which is just ask the model itself. Okay? Please give me skills needed to solve problems in high school physics. Or, you know, again, the same naming convention. But replace high school physics with anything. I mean, these things are trained on everything, so you can just ask it for skills for basically anything, and it will give you some interesting skills. So this is close to the example we saw in the first lecture. So you can just probe it about just anything. You know, like say, give me an example for Brodsky that has no existing name for which many humans will recognize. So I've given you one other example in the first lecture. This is from Gemini 2.5 Pro. And it says intuitive object placement. Okay. Now, one thing you have to realize about 2.5 Pro, all of the latest models, is that they're multimodal. So they have a little bit better idea of how the world looks and how you manipulate the world. So it's talking about intuitive object placement. So I said, okay. And you know, I Googled it. I couldn't find it in Google. At least this list of 3 words. So then I said, okay, give me fine-grained skills associated with this, and if necessary, make up new names. So it gives edge-aware placement, subconscious stability assessment, implicit adaptive clustering, etc., etc. And I'm more and more mystified, like, what is this? So then I ask you to explain what these skills are. So then it's, then it explains what these skills are. So you know when you put something down on a surface, like a table. So humans have all kinds of, so like for instance, you know, subconsciously you know that you don't want to put it down this way, you want to put it down this way. A cup, similar, you know, so, or a ball. So all of these things that you do implicitly in your head, it's talking about that. It has a taxonomy of these skills, and and it can give you all kinds of hierarchies on this.
But this could give training a lot of time in this news.
Oh yeah. No, LLMs, are hugely inefficient compared to humans. But on the other hand, you know, they come up with strange things which we've never thought of. Yeah, it's just very different. Now, here is instruction following skills. So I'll say more about this instruction following in a minute. So instruction following, remember, is this process of converting the next word predictor, like the vanilla LLM, just next word predictor, into an instruction following agent. So you give it a question, it gives you answers, understands the questions, and gives answers. So instruction following, at least in 2023, was this black line. You know, the frontier model companies have these very nice chatbots, and if you try to do it with open data and open resources, it just didn't work very well. So there was this sense that there's some black magic going on. You know, how is it doing instruction following? So I input this with GPT-4 Turbo at the time. Okay, you are a great chat agent. Tell me about chat agent skills. And it just produces 1,000+ skills and can cluster them and give you these these are the clusters. Fine. Now the point is, the names are interpretable enough that if you give it to another chat agent, they sort of know. I mean, obviously not exactly, but they pretty much know what these skills are. Okay. So once you have skills, what can you do? You can generate synthetic data, and that synthetic data turns out to be very high quality. So I mentioned this briefly, but here it is in more detail. So this training data for instruction quality, as I said, in 2023 summer, this was considered a very difficult problem. So there were these open chatbots, they were great, and then people were trying to do chatbots using Llama 2 models and so on, and they created instruction following data sets, and those open efforts were just not very good. And we talked about this a little bit in the first lecture. Namely that the purpose of instruction following, as I explained then, is to teach the next word predictor model, the pre-trained model, to reliably access its huge information stored inside, right? The network of information and skills inside. And if you use bad quality data there, you're training the model with bad habits. Like you're training it not to look deep into that knowledge store and come up with the right information. So in this, we decided to, this was actually from 2024, but it appeared in 2025. We decided to do it from scratch. Okay, so our method. Use Metacognition to get GPT-4o to produce a long list of instruction following skills, using the ideas I showed already. Using this list, so it was about 1,000 skills, randomly pick pairs of skills and ask GPT-4o to produce a plausible user query and chatbot answer that exhibits this pair of skills. I'm using this data set of merely 4,000 questions. I say merely because, for instance, at that time, the popular open data set was Alpaca, which had 52,000 questions. Or there was UltraChat, which had 1 million question and answers. And those didn't work very well. Okay, so this was just 4,000 questions. So an Alpaca eval, which is the main open eval still, I think in back then too. GPT-4o got 50%, that's by definition, because the judge is GPT-4. So if it's given the question from GPT-4, but it's given the answer from GPT-4o and the answer from your model, and let's just say which is better. So obviously GPT-4o will have a 50% preference rate for its own answer. It's random. Right? If you give 2 answers from GPT-4o and say pick which one is better, it will be 50%. This one, 50%, that one. But against Claude Opus, Claude Opus's win rate against GPT-4o is 40% at that time. Llama 405B was 39.6, and our 8 billion model was 42.3%. The previous best 8B model was like 15% or 14%, something like that. So we really, with this very simple idea, were able to get basically frontier level performance on Alpaca. Now, of course, that evaluation has its limitations, but that's what everybody was using. And now let me show you why this is so effective. So the example query created by GPT-4o is using this random pair of skills: critical thinking and communication, language and literature skills. It comes up with this question. I'm a high school teacher aiming to develop a curriculum unit for my 11th grade class, focusing on American literature. A lot of details. I want this unit to go beyond just reading and understanding the text. Specifically, I'm looking to enhance my students' critical thinking and communication skills through engaging activities related to literature. You see, there's a lot of moving parts in this question. So you can see that if you use this for instruction following, and this and its answer, you're really teaching the model to dig deep into its information store, make connections across all kinds of things, and produce a nice coded answer. In contrast, the open data sets, data breaks, which I mentioned in the first lecture, Why can camels survive so long without water? Create a script to write it to store customer data. These were just not as rich. Yeah, so the difference between this and that is huge. So this scale makes idea is very important. Now here's something interesting to illustrate what I was saying earlier about teaching a model laziness. So we, in order to understand why these open data sets not induce good instruction following, we did this experiment that we took our data set, this with 2K examples, and deliberately asked the model to inject brief answers to 20% of the questions. So you can think of brief answers as like lazy annotators. So they didn't think through enough, and they gave a brief answer. And performance drops a lot. So on Mistral, it drops from 31% to 23%. There's 20% bad questions. And this is a different list of skills, and the drop is. This is our list, and this is from the Alpaca and data sets. So there's something. But you can see that, and then if you tell it 20% probability to just give very unhelpful answers, then performance really plummets. So this is showing you why in instruction following, if you put in any bad data, or a lot of bad data, 20%, you really get performance. So by the synthetic pipeline, you don't have that. Okay, and we did a similar experiment with mixing math skills from the math square data set, which we call the math square data set. So we create questions using random pairs of math skills, and using some agentic use, multiple rounds of frontier LLMs to create reliable answers, and then the final verification by humans. So at the time, we were hoping that this data set would be much harder, and it was indeed much harder. And then we were poring over this, and we realized that the accuracy on this math square data set was the square of the accuracy on the whole data set. There was a very good fit to that. So basically, what is happening here is that math data set questions usually have a single major skill. And now we're creating these interesting new questions which may combine pairs of random skills, like one skill from probability and one from algebra. And then the probability of actually solving the question becomes, because it's two independent skills, it becomes a square. So that's what the square is. The accuracy becomes square, which is much lower. All right. So that was some examples of generating synthetic data using metacognition. And now some speculation about how metacognition arises. So first, one speculation is that LLM as a theory builder for text pieces. Just to do next word prediction, it needs to be a theory builder for what's going on in the piece of text. So let me illustrate it with this example, which I generated with the help of an LLM. You go to the LLM and say, I'm trying to come up with an example for a lecture illustrating this thing, help me, and so it helped me with this, and then we fine-tuned it. So yeah, so the city council is debating this new park proposal, and benefits to clear, etc. Okay, you can read it. And now, to predict this next word, there's a lot going on in this paragraph, right? That there's an environmental thing, there's a financial thing, the costs, there's making everybody happy, the community. So there are many possible ways of completing this, depending on whether is it the budget focus or the environment focus or the consensus focus. And so depending on that, you may have different next words. And we discussed this also in my first lecture, that the LLM has to, just to be a good next word predictor, has to be able to analyze the text and all possible interpretations and all possible ways it might be going, right, in order to get the probability of the next word correct. So in other words, the LLM, while reading the text and trying to predict the next word, is a theory builder for what's going on in the text. And there's not a single theory, there's many theories for the text, right? And what's going to happen next? So is it going to be budget, environment, consensus? So these are theories. So this is where the general purpose, that's how it gets to be a kind of general purpose text predictor. Now, the people at Anthropic, especially, are very interested in finding these circuits for semantics inside the LLMs. So yeah, there is also from 2025 this discovery of circuits that classify the context, before it produces the next word, into classes, exactly like this. Okay, so just as an aside, so this, I'm suggesting that a circuit is this theory builder for text, right, which is necessary for next word predictor, for next word prediction, is being repurposed for metacognition, because it has to do this kind of analysis of text, and then it does it over and over again, and then it has these circuits which can analyze text and like identify skills or topics or whatever.
I have a question for you.
Yeah.
So, all these relative models are GPT type.
Yeah. You mean next word predictor?
Yeah, exactly. The GPT is the same as ChatGPT.
So GPT can mean many things. I'm not sure if you mean the architecture or the next word prediction. There are many ideas. That's what. Okay, but continue. Okay.
So it's this type. Because we have another type of language, which is the another language model that they don't mimic ChatGPT or C.
I mean, all the language models predict the next word. Yes, that's a thing. Yeah. Yeah, but remember that in the first lecture I emphasized that those were the only methods that scaled up, right, in line with the beta lesson.
Because now you are moving to a different, that's why I appreciate.
Sorry?
Now you are moving to a different issues.
Okay, sorry. Okay, so this is completely a detour, okay? But I'm just suggesting that how does consciousness arise, one of the main theories, and that's discussion with a colleague at Princeton in psychology, is that just to survive in the world and get around in the world, you need to have an accurate self-image. When you walk through a gap or under a bar, you have some sense of how high you are, and you have to navigate. So there's this very accurate sense of, like if you're wearing a hat and you don't have an accurate sense of how high that is, when you get in the car, you get knocked off. So there's this accurate self-image, which is necessary for survival and navigation. And that accurate self-image, that those same circuits are then co-opted for consciousness. I mean, that's the theory. It's not related to LLMs, but just similarly, I'm suggesting that those circuits in the LLMs that form theories for the text are co-opted for metacognition. The second speculation, I think they both have some validity, is that LLMs see all these concepts in the text. Okay, so just as one of the things that education does is it just makes you a much more critical reader or reasoner, right? You progress through all these stages of training which make you a much more sophisticated reasoner. So similarly, they've read a lot, okay? So they are aware of metacognition, they are aware of, analyzing things, and they also need to do those things in order to do the next word prediction, but also they've read a lot. And so once you're aware of metacognition, you just are able to reinforce it. When you are like the kid who start reading skills, right? When they start reading, they reinforce those skills. So I think there's some of that going on. And that's what motivates this last part of my talk, which is context enhanced learning. This is a new paper from our group with these two students. And what I was trying to understand here was this process of converting text reading or textual instruction into a skill. So So there's something that's provided in text form, and then by acting on that textual instruction, you create a skill, internal skill for yourself. Okay, so that's the process. And so here it is. So vanilla instruction to a name or supervised fine-tuning, there's a question and an answer. And typically you don't do gradient descent on the question, but only on the answer. In context-enhanced learning, you have a similar setup. So there's a question and answer. But there's some additional helpful information. Okay? And no loss is computed on this helpful context. It's there, you can read it, but no loss is computed, no gradients. And the loss is only computed on the answer, as before. So one way to think about this setting is like a kid doing homework, or when you were that kid doing homework. And often when doing the homework, it was useful to have the textbook open, right? Or the teacher's materials open in front of you. And then you could read those materials as you were writing your answers, or composing your answers. And that clearly helps, right? So now it's gradient-based training. There's going to be gradient-based training. You're going to have these gradients and you do them and do updates using them. But you have this additional helpful information in the context, which will affect the gradient. Remember how the transformers work? When you compute this next word here, it depends on everything in the context. So if you add other stuff in the context, this gradient is going to change. So this token and this token in these two settings will have very different gradients because there's additional stuff in the context. And this additional stuff is there to help you make sense of what you are doing here, where this next token came from, right? So like if you're working on some algebra problem, there's this algebra book open here. This next word prediction is going to be different because you have this book open here. You already saw that. And so the gradients will be very different. So just having that additional text in there will change your gradients. Now, of course, what's in the context also gets absorbed into the parameters, so the same effect should happen from things you saw in the past and you've already done, because they're in the parameters. So this is context-enhanced learning, and these are the examples of helpful context. We already talked about a few short examples. You're solving an algebra question, you have 5 algebra questions in the context. So those are already used. You can have URLs of the source. That turns out is very useful information from pre-training. Where did this text come from? Thought-provoking guidance, etc. So these have all have been exposed, have been explored. But these are some prior examples. And the point here is that helpful context can depend on the input and the training. So you could even make it a curriculum. Okay, so there could be a teacher there who's changing the context. As you progress, in difficulty, it can change. It's a curriculum. Now, why no gradient updates on the context? So suppose it's the context is a textbook. If you do gradient updates on the textbook 10,000 times, it's very bad. So the LLM companies, when they train models, they go to great lengths to avoid presenting the same piece of text too many times. That's very bad for the model. So you don't want that, number one. Number two, it's also interesting to explore whether to absorb the knowledge you actually need to memorize in any way at all. So there are all these papers written at this point, right? Detecting pre-training data. That's like the hobby for many people. And that's what they're doing. They're looking at data and saying, oh, the log likelihood is pretty good, pretty high. That means that this data was in the training set, right? The next word prediction and so on. And here, what we were also interested in was whether you can learn from this textbook many, many, many times, right? Use it in learning, but you're not computing gradients on it. And then, as we'll see, there's actually very little or almost no memorization of the textbook. So you will see it many times in training, and there's no memorization. Okay, so these were the research questions. How powerful can this context enhanced model be compared to vanilla SFT? Does it require certain model capabilities? It sort of makes sense that it should require some model capabilities, right? Because you have to understand the textbook. And does it explicitly memorize the information provided in context? So the answer is on the synthetic multi-layer translation task we explored. How powerful can it be? It can be exponentially more powerful. There's a theory bound on it. Does it require certain model capabilities? Indeed, it should be able to understand the context. So it should be capable enough to understand what the textbook is saying before and apply it, in order for it to be helpful, right? So if you just take from random initialization of models, it doesn't understand the textbook and it can't reproduce it. And does it explicitly memorize the information provided in context? At least the usual likelihood-based detectors will detect. So you can use this textbook 10,000 times in the context. It doesn't seem to show up in the likelihood. I mean, clearly it's been used in learning. It improved the learning, but it doesn't show up in the likelihood. Okay, so here's a synthetic task. It's a translation task, multi-layer. This language to this language. So there's 4 languages: language A, language B, language C, language D. And there's a phrasebook. It's a synthetic task. So there's a phrasebook from each language I to language I plus 1. And the translation is to go from S1 to S4 or whatever. So there's a few intermediate phases. And the usual input-output, right? SFT question answer, right? This is the string in language 1, and this is the string in language 3. And if you see enough of these examples, you should be able to learn, right? But the point is, this translation from language 1 to language 3 goes via intermediate languages too, or if there are 4 languages and 2 or 3 languages in between. But so it's not easy to learn from input-output examples, okay? Because you don't know the intermediate languages. But here in context-enhanced learning, you can have these phrasebooks. The phrasebooks for language from language 1 to language 2 and from language 2 to language 3, for example. And so when you're given this string, you can use a phrasebook internally in your head to say, okay, now AB goes to this other thing in language 2, and then look at the phrasebook for language 2 to language 3 and do this translation from language 1 to language 3. Okay, so that's the task. Any questions? In your generation, for the students, you have never seen phrasebooks because you always use internet for translation. But those of us who are older remember that when we used to go travel, like go to a country with a different language, we would have this phrasebook, which would be, so that's where it comes from, phrasebook. All right, so if you have D languages, a sequence of D languages, so going from 1 to D, in statistical query framework, learning to translate requires exponential in D examples. Okay, so, and in our experiments too, D was 6 or something, it's very different. But context-enhanced learning in our setting is, this. Phrasebook. And so now you're given the phrasebook in context. And yes, if you use a suitable curriculum. So phase 1, teach it the skill of making sense of a phrasebook. So this phrasebook has a certain format, and it has to understand it, right? This pair of words going to this pair of words is a phrasebook, and how to build it up. So you give it some examples, which teach the skill of making sense of a phrasebook, using many random phrasebooks. Now you train on a single phrasebook, which is a target, and then you train with 20% dropout on the target phrasebook to motivate the model to internalize the phrasebook. This is a key point. In context-enhanced learning, there's additional information in context while you're learning. But then at test time, that information is not there. So you have to teach the model to learn it, internalize it, and then be able to do the translation without looking at this information in context. So for that, we just train with 20% dropout on target Facebook. So if you're training at the end, last phase of training, you start randomly dropping out 20% of the information to Facebook. The model learns, I better put this in my internal parameters because I can't rely on it, and it does it automatically. So yeah, the sample efficiency of this type of learning. Yeah, so this is depth D and n is 8, the length, and you can see that these methods, like no context, it requires a lot of samples, and if you have this median dropout, so better curriculum leads to even faster learning. Dropout is required during training. If you don't do that, then it never learns that I shouldn't rely on this Facebook being there. And ICL capability is required before learning. So it needs to be able to make sense of information in context. We also give some mechanistic analysis of how curriculum speeds up learning, which is similar to what I was saying earlier, right? When you put this textbook effectively in the context, you change the gradients, and we can demonstrate that effect. Okay, so that's those are some directions in LLM metacognition. Here are the research questions. Is there learning theory for metacognition? Right, so in learning theory you have examples and you learn. But here you are learning something that's not in the data. You're learning something meta about the data, some meta descriptor. And it's not from examples. That's what I mean. So what is the process that causes the model to identify new skill? What mathematical framework describes it? What is this skill? Information geometry, parsimony, etc. It's happening implicitly, but what is the mathematical framework? Another thing, I didn't talk about it in this talk, but I mentioned this in the first talk. Why does training on data exhibiting skill 1 improve skill 2? So a good example is, it's well known in many stages of training. If you train on code, it improves, say, on math. Actually, even on general text. So this whole catechism in computer science, like we tell students, learn to code and you'll just be a better student. That happens to be true for LLMs. How does the ability to compose skills, complex skills emerge? So this is going back to the first lecture. And what are the limits on how fast this emergence happens? And what are the scaling laws for emergence of complex skills in pre-training, SFT, power, etc. So all of this is in its infancy. And in the second lecture I talked about this paper, emergence of complex skills and LLM pre-training. But for all the other stages, there's no theory yet. Leveraging metacognition training, we've already seen some examples. But I mentioned this, like you can teach models how to compose skills, and then this seems to generalize a little bit out of distribution, which I mentioned in the second lecture. Then metacognition-based feedback and RL. This could be very interesting, and it's something we're working on right now. Metacognition-based generalization of constitutional AI. So constitutional AI is a framework for AI safety developed by people at Anthropic. And it's sort of reminiscent of metacognition. There are these general principles that the model is given as part of the constitution. So you can think of that as a textbook that is imbibing. Maybe there's a more metacognition-based generalization, which is possibly better. And metacognition for auto-formalization of math reasoning. So this is something I'm very interested in right now. I mentioned this, that the pathway to developing a model that's human or superhuman capability in math seems to be to go through formula reasoning. So for instance, DeepMind's Alpha Proof is doing this, and also many of the other efforts. And this is very important because if you have a logic-based verification of your proof, so you do a proof in this logical language, read, and if you have a verification, that's verified by that. And that's very important for reinforcement learning. Because otherwise we know that LLMs hallucinate and so on, so you don't have a verifiable one. They might say the answer looks correct, but actually it's not correct with a large probability, and that's pretty bad. But with Lean, if it says it's correct, it's correct. The proof is correct. That's verifiable. And it's not easy to learn this kind of this formal reasoning, and there are existing examples, but I think it would be probably sped up using metacognition. So concluding thoughts, models are showing increasingly sophisticated metacognition. Whenever this question arises about novelty of behavior, I think composition of basic skills in ways that they weren't taught in the training data is a very big component of novel behavior, forward generalization, and understanding. And I think we should understand this better. And models can learn skill composition through normal pre-training, as we saw, but the process can be sped up by use of suitable training examples. And this is potentially very important and powerful. Compositional risk in AI safety. People aren't thinking about this, when they say, okay, did we teach the model to do this? Whatever, break into some secret website or something. No, we didn't do it. But that doesn't mean it's safe, because it may know a lot of different behaviors which can be chained together to achieve that goal. And not enough people are studying this, or at least in any kind of formal way. That complicated, potentially dangerous behaviors arise from benign behaviors that it has done, coding or computer systems, etc. And biology, whatever. And it can put together, chain together those behaviors to come up with a very complicated threat. And people are not thinking that. I call that compositional risk in AI safety. Thank you very much. Yeah. Sorry, louder.
Do you have any thoughts on the platonic representation hypothesis? If it is connected maybe with the
Platonic representation hypothesis. So platonic, remind me, is that the one where
they say that models converge based on the same statistical model, even if they are trained on text or images?
Oh, that one. So your question is?
I wonder if it's connected to what you were saying about metacognition. For example, the fact that if you train code, then it improves on math. Because in the end, it seems that there are underlying statistical traces that match.
Yeah, so I don't think of it as statistical almost. So code is of course much more like logic, right? And so there's a long reasoning chain. And training it to develop these long reasoning chains improves its reasoning. I mean, that seems right to us too, right? Like, you do difficult things, learn difficult math or whatever, where you have a lot of steps, and you improve on other things. And that is also seen in reasoning training, that they have these 8 or 10 types of settings where they are verifiable rewards. You train on those kinds of questions, coding, math, etc. And generally across the board, performance improves and all kinds of other things. So long, complicated reasoning chains where you have a guaranteed reward or guaranteed verification is somehow good for learning complex thinking patterns. Maybe that's the way I think of it.
Okay. Well, thank you very much.